I put this one together as kind of a demonstrator. It's just I was primarily looking for something that would test the cell's durability, longevity, and so forth. All the cells are the same. I mean, they're just, you know, they're very thin, and they've got the semiconductive crystal in between. It's a thermogalvanic semiconductive device. I do have a provisional patent on this so far, and which I will finish up and get the utility patent this year. So what I've done is I've mounted this double pendulum motor on here. It's been running for a little over a month, but I had to put this potentiometer on here because even though, you know, this draws some power, this produces more power than this really needs. It's 6 inches square, and really I needed something that was just kind of the size of the base of this thing, or maybe 2 inches square, just something small. And you can see if I reduce the resistance in the potentiometer, you hear it going click, 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 click. Sounds kind of like a clock. It's only because the pendulum is slamming against the plastic supports on this side and the other side. So it just, you know, I mean, if I turned it all the way up and those supports weren't there, the thing would just spin around and round, but probably not, because this is sort of a flip-flop circuit here. There's a couple of transistors on there and some other components, tiny little capacitors, and there's another one down there, and I've got these connected so they're in synchronization, so it works really good as a test module. But all these cells are the same. I've got lots more that I've manufactured, and I've got lots more coming that I'm working on too, but they're all identical. They all output about the same amount of power. This particular one that's been running this for all this time, well, now I should put the resistance up a little bit so it doesn't hit it too hard on that. But you can see that the cell is outputting 1.442 volts while it's under load running this pendulum motor. And I've got some ideas to do. Well, actually, I'm working on a rotary one that's kind of like this, but it's small, and I've got more important projects to do, because what I want to do is these cells will be combined in series parallel, and the idea is to run all my different quantum magnetics machines so that you don't have to rely on solar or wind or batteries. And that's pretty much the idea, since these run for so long and they're powerful enough to do it. I did get the patent because got the provisional patent because there's nothing else quite like these. So, I mean, it's not like your traditional crystal cell type batteries, whether it's a powder or a salt crystal that's been heated, and you got copper and magnesium and all that. So these are unique in the fact that the thermal part is, because it's a semiconductive crystal inside, and the number of free charge carriers actually increases with temperature. So, again, even with just the heat of my hand on this cell, you'll see the voltage rise, and we'll do that in just a second here. And then I'll take it outside and I'll show you what the sun does. Even a campfire or a match, anything. But it doesn't rely on that. It's not like these Peltier type thermoelectric devices, which are very expensive, and there's two dissimilar metals in between, and a couple of ceramic plates and some dopes and different agents, to make this thing work. But it takes a really high temperature gradient from one side of, let me set one down, from one side to the other side. And unless you're really burning up a lot of energy and you've got something that's producing a lot of heat, or it's a fire or boiler or whatever it is, the sun's just not enough. You need some really high temperature. But that gradient, it takes a lot of energy. So these things is like, okay, useless. All right, no good there. But these operate at room temperature and also get even better if the temperature of the room is warmer, or they're close to a warm source, or they're in the sun, or anything like that. So we'll move forward and I'll show you the heat on this one. Okay, now obviously this cell is not under load, and its standing voltage output is at this point 1.573, 1.574, but watch how that changes with just the heat from my hand in a matter of seconds. Now I'm not putting pressure on this, I just want the heat transfer. again, that's just my hand, just the heat from my hand. You see how it just continually comes up. Now something that's warmer than that, a warmer source, a candle, campfire, the sun, anything warmer than my hand is going to increase the output, and it'll hold it. I mean, it'll lose some when you put it under load, of course, while it's powering a device, but pretty amazing that, you know, again, the number of charge carriers increases with that temperature, just a little extra temperature on there, and it transfers through into the silicon crystal through the graphite just, you know, immediately. So it's a fascinating device. See, it just continues to go up, and again, just nothing but my hand. Okay, I'm shading the panel right now because I want you to see how this rises. Hopefully we'll get this in the frame. Okay, now watch the sun. We're outside in the sun, and the sun's hitting the surface of the panel. I'm sorry, can you see that? So you can see how much faster the output will rise with a little bit warmer surface. In this case, just some sunlight. Now it doesn't matter if these panels are all stacked together and connected together, which I'll show you later in series parallel for whatever your purpose is, but it'll still do the same thing. Even in a warmer environment, it does the same thing. If we stayed out here for a few more minutes, which I won't put you through, it'd probably rise up to about 1.7 volts, somewhere around there. These cells like to be anywhere from around 1.5 to 1.7 typically. Sometimes they drop a little less than that depending on the temperature, but they operate, you know, where it's cold, as well as operating much better where it's warm, because of the charge carriers increasing thermally in the silicon crystal. It's almost 1.6 coming up on it. Anyway, wanted to show you that. Now let's cut away to this for just a moment. Everything that you see here was part of my early silicon crystal study. Let me just zoom in on this so we can get this more in frame. Okay, everything that you see here, all these different odds and ends, all produce electricity. I know that sounds hard to believe, but they do. I've made everything except for this particular piece here, which is a piece of lava rock that I picked up on a freshly cooling lava field in Hawaii. And at first, when this first cools, it has a very silvery, almost chrome-like appearance to the surface, and then it gets shiny, and then it eventually gets dull. But with a little dope, it actually generates electricity. I'll keep it in the frame. And not a whole lot. You can see here, if you probe it right, sometimes you can hit spots that'll produce 200 or 300 millivolts. So, you know, not a whole lot of power, but obviously I'm not hitting the right spots. But you can see that it definitely will generate electricity as it zeroes back. Okay, all these other parts, this here is kind of like, oops, let's see, can you see that? This here is kind of like the lava rock in a way. I heated this to, it was over 1,000 degrees, and it's got the same kind of texture as the lava rock. Also produces electricity. There's no metals in these. I mean, after all, this is just overheated silica. Think about it. It's just really amazing. Now, these little pieces, they're very, very tiny, as you can see. This is about half an inch square or less. Now, I actually used magnesium on this, but it does have the silicon crystal center, and watch what the voltage is even on this tiny little cell. Let me get it on there. There we go. 1.784 volts. 1.78. That's pretty darn good. Now this one here, this one's interesting because I made a mix, and this is a little plastic tray that I poured the mix into. As you can see, it's very shallow, and you can see the level of the mix where it hardened and solidified on the bottom. But then overnight, just in ambient air, it foamed up. It did this thick foam that you see, and it was almost like lava rock in the beginning. It was very chrome looking, very shiny, quite interesting. There's no metals in here. There's no copper, magnesium. There's no metals at all. It's just the mineral mix and silicon and so forth. So, but just to show you what it does as just a foam, this is an electrical foam. This is electrical producing foam. Can you imagine? So let's just take a look on the meter and see what we get here. Okay, 0.62 volts, 0.60 volts, 0.60 volts from some foam. You see why this was so interesting to me? I thought, wait a minute now, this is really fascinating. So I used some of the same mix, and I put it between just like this. I had a little piece of magnesium and some graphite, and here it is. I put the mix in there, but the hydraulic, let me get it in the camera if you can see this here, but the hydraulic pressure of this was so great right here that it absolutely split. It split that in two. You see? It split in two. And yet, and look how thick that is. I mean, it's amazing, and how small it is. That took a lot of pressure. Well, that was this same foam. And this stuff is this foam, it's as hard as rock. I mean, it's just as hard as rock. And yet it's a foam. I mean, I put my probe through here. You can see these, you can see the holes that I just had, you know, kind of drilled with a meter probe. See, it's in the hole. So you're able to go through it as a hardened foam, but it's still foam. And so anyway, let's go back to this broken one. But even the broken one on the meter, you can see that it outputs 1.17 volts. And that's with the piece broken on the top, separated. So, you know, this is amazing stuff. Now, this one here doesn't have any metals in it at all. It's just some of the crystal. It outputs electricity. But I thought you might like to see this because this is very interesting that you know, other than these three pieces here that have some magnesium, there's no metals in this other stuff, and it still produces electricity. So we've still got a lot to learn.